Nitroglycerine is an explosive which, on detonation, decomposes rapidly. To form a large number of gaseous molecules, the equation for this decomposition is given below. A sample of nitroglycerine was detonated and produced 0.350 grams of oxygen gas. State what is meant by the term 1 mole of molecules. So 1 mole is Avogadro's number of molecules. Or you could say it's 6.02 times 10 to the 23 molecules. Calculate the number of moles of gas, oxygen gas, produced in this reaction, hence reduce the total number of moles formed, the total number of gas moles formed. So we want the moles of oxygen gas. We've been given a mass, and we can work out the MR. Don't forget there's 2 oxygen atoms, so it's going to give an MR of 32. So that gives us 1.09 times 10 to the minus 2. We then need to work out the total moles of gas. So if we go back up to the equation, we can see that all 4 of the products are gases. So in terms of moles, the total number of moles is going to be 12 plus 10 plus 6 plus 1. So we've got 29 moles of gas in total. We know that 1 mole of oxygen is equivalent to 1.09 times 10 to the minus 2. So 29 moles is going to be 29 times that. So that gives us total moles of 0.316. The answer should be to 3 significant figures. If you have made a mistake earlier on in the question, but you've done the right method, so you've times whatever your moles were by 29, then you're going to get quite consequential marks for this particular answer. Okay, we now need to calculate the number of moles and the mass of nitroglycerine detonated. So the first thing we need to do is work out how many moles we've got of nitroglycerine. So if we go back to the start of the question, we can see that 1 mole of oxygen comes from 4 moles of nitroglycerine. So the value of moles of nitroglycerine is going to be 4 times that of oxygen. So it's going to be 4 times 1.09 times 10 to the minus 2, which equals 0.0438. Make sure you write your answer to 3 significant figures. Then to work out the mass, it's going to be equal to the moles times the MR. The MR isn't given, so you're going to have to work it out. And you should work it out at 227.0. Remember, all MRs should usually be written to 1 decimal place. So the mass is going to be those 2 numbers multiplied together. And the answer for that should be 9.90. Remember, it's only to 3 significant figures, so when you round it, it will go up to that. And it's a mass in grams, so don't forget to put your units. You're not penalised for units in this question, but it's good practice to put them in. A second sample of nitroglycerine was placed in a strong sealed container and detonated. The volume of this container was 1 times 10 to the minus 3 metres cubed. The resulting decomposition produced a total of 0.873 moles of gaseous products at a temperature of 1100 Kelvin. State the ideal gas equation. So a nice easy mark to start with. PV equals nRT. Not much to have to do to get 1 mark. We're now going to use it to calculate the pressure in the container after detonation. So the first thing to do is to make sure you can rearrange the ideal gas equation. Then you need to substitute the numbers in. So the moles are given in the question. R is the gas constant, which is also given in the question. The temperature is given to us in Kelvin, so we do not have to change it. And the volume is given to us in meters, so we don't have to change it. So this is a very straightforward ideal gas equation question. There's no conversion of units needed at all. Now remember, the answer comes out in pascals, so in this case it is a very large number. So it may make sense to convert it into kilopascals or even megapascals. So you divide by 1,000 to get it into kilopascals, and by another factor of 1,000 to get it into megapascals. If you are uncertain about converting units, leaving it in pascals would be fine. To neaten it up, it could be written in standard form. Titanium 4 oxide is used as a white pigment in some paints. The pigment can be made as shown in the following equation. We want to work out the percentage atom economy. And it's for the formation of titanium oxide. So the first thing we need to do is put on the top row the mass of titanium oxide, and this is the only time you would times it by the number of moles. There's only 1 mole, so we're just going to put the MR in. We're then going to divide that by the mass of all of the reactants. So we've got 1 lot of titanium chloride and 2 lots of water. If we add those together, we get 225.9. Don't forget it's percentage, so we're timesing it by 100. And that gives us an atom economy of 35.37%. In view of the low atom economy of this reaction, suggest how a company can maximise its profits without changing the reaction conditions or the production costs. So in this case, we need to see what else is made. And we're making HCl, so if they can make some money out of that, then they're going to be able to reduce their production costs. So the answer would simply be sell the hydrogen chloride that's made. In an experiment, 165 grams of titanium chloride were added to an excess of water. Calculate the moles of titanium chloride in 165 grams. So we're going to use mass over MR. So the mass given to us in the question is 165 grams. The MR you're going to have to calculate, and that comes out at 189.9. So that gives us 0.869 moles. It's 2 marks for this question. You get 1 mark just for working out the MR. Calculate the maximum amount in moles of titanium oxide which can be formed in this experiment. Now in the first bit it tells you that it's added to an excess of water. That means that all of the titanium chloride has definitely reacted, and the equation is 1:1. So the maximum amount of moles of titanium oxide are going to be the same as the amount of titanium chloride that reacted, which is 0.869. The maximum mass of titanium oxide is going to be moles times MR. The moles we've worked out in the first bit. The MR is 79.9, so that gives us a maximum mass of 69.4 grams. In this experiment, only 63 grams of titanium oxide were produced. Calculate the percentage yield. So this is a nice question. It's taken us through it step by step. This is our maximum theoretical yield here, and we've been given the actual yield, so the percentage yield is always what we actually get in the experiment, which in this case is 63.0 grams, divided by our maximum theoretical yield, which we always have to work out doing a moles calculation, but we've done that above. And then it's a percentage, so we're going to times it by 100. So the percentage in this case is 90.75%. A metal carbonate reacts with hydrochloric acid as shown in the following equation. We've been told we've got a sample of the metal carbonate, and we've been given a volume and a concentration of the acid. Now in terms of where we can start with this question, we don't know what M is, so we can't do anything with the mass to start with. The mass is going to come into the question later on. The only place we can start is with the HCl, and the first part of the question asks us to calculate the moles of HCl. So it's a usual vol times Gonk calculation. So if you put the numbers into your calculator, you should end up with a number of moles of 0.013. Okay, we now need to calculate the amount in moles of the metal carbonate. It says in 0.548 grams. That's a little bit of a red herring. That is just the mass that you were given in the question, so don't let that one throw you. We need to go back to the previous part of the question where it gives us the equation, where it says the metal carbonate reacts with the hydrochloric acid in a 1:2 ratio. So the moles of the metal carbonate are going to be half that of the hydrochloric acid. Which should come out as 0.0065. Right, we don't know what M is, so we want to try and work out the MR, and this will help us identify M. So we're going to use MR is equal to mass over moles. Now the mass we've been given in the question, that was the mass of the salt that was weighed out, and we've worked out the moles in the question above. So that gives us a mass, or an MR, of 84.3. Okay, so now we know that MCO3 has a mass of 84.3. We want to find out what just the M is. So we want to take away from it the mass of the carbonate. So in effect we're doing MCO3 minus the mass of the carbonate. So that would be 84.3 minus 60, which gives me 24.3. We're then going to use the periodic table and find out which metal element, because we know it's a metal, has a mass closest to 24.3. And the one that I think is closest is magnesium. Now, if you weren't able to do part of the question, you can see they have given you an MR to use. So if you were to do this same one but using their MR, you would get a slightly different element, but you'd still get full credit for that. And that element would have been strontium. There are several oxides of nitrogen. An oxide of nitrogen contains 25.9% by mass of nitrogen. Determine the empirical formula of this oxide. So we know that nitrogen is 25.9%. The only other thing that's present if it's an oxide is oxygen. So we can work out how much oxygen we've got by doing 100 minus the percentage that is nitrogen, which gives you 74.1%. And you get a mark for just working that out. So we've now got to work through the empirical formula. So I want to divide those masses by the relative atomic mass. And the same for oxygen. Now to convert those into whole numbers, divide them both by the smallest number. And you end up with a 1 to 2.5 ratio. Well, we can't have fractions in an empirical formula, so to turn them into whole numbers, we're going to multiply them both by 2. And that ends up with the formula N2O5. And that is our empirical formula. To work out the MR from the empirical formula, the first thing we need to do is to work out the mass of the empirical formula. So if we add up 2 nitrogens and 5 oxygens, we find that the mass is 108. So in this case, the empirical formula only goes into molecular formula once, so it's the same. If the value was a half, we would double the empirical formula. Sodium carbonate forms a number of hydrates of general formula Na2CO3X H2O, where X can be any whole number. So for every one lot of this, you can have any number of waters associated with it. A 3.01 gram sample of one of these hydrates was dissolved in water, and the solution made up to 250 centimetres cubed. So there's our first volume that we need to look at. In a titration, 25 centimetre portion of this solution, so notice we've got a factor of 10 between those two already, required 24.3 centimetres cubed of 0.2 molar hydrochloric acid for complete reaction, and it gives you the equation. So we've got lots of information there. Let's have a look at what the first bit actually asks. We need to calculate the number of moles of HCl in that volume and for that concentration. So it's a straightforward vol times conc calculation. Okay, and that gives us an answer of 4.86 times 10 to the minus 3. We then want to deduce the number of moles of sodium carbonate in 25 centimetres of the sodium carbonate solution. So we need to go to our equation and see how the two react together. And you can see 1 mole of the sodium carbonate reacts with 2 moles of the hydrochloric acid. So the moles of the sodium carbonate are going to be half that of the acid. Which is 2.43 times 10 to the minus 3. Okay, if we have this amount of moles in 25, then we're going to have 10 times that in 250, because 25 goes into 250 10 times, so the same is going to be true for the number of moles. So it's going to be 243 times 10 to the minus 3 times 10. Okay, so we then need to work out the MR. Now to work out the MR, we're going to do mass divided by moles. Now we've worked out the moles. The mass is given to us up here in the question, so we're going to use that mass. If you ever think you've got a piece of information missing, always have a look back in the question, because you'll probably find the bit of information you're missing will be there. So that gives us an MR of 124. In an experiment, the MR of a different hydrated sodium carbonate was found to be 250. Use this value to calculate the number of molecules of water of crystallization X in this hydrated sodium carbonate solution. Right, so we're going to have a look at this. Now we know the total MR of that is 250. What we can work out using the periodic table is the MR of just that bit. And if we were to take that away from the whole, that should tell us how much of it is water. So let's do that. So the MR of sodium carbonate is 106. So the MR of XH2O is going to be 250 minus 106, which is 144. We need to see how many lots of water we have in 144. So to work out X, we're going to take the 144 and we're going to divide it by the MR of water, which is 18. And that goes in 8 times, so that must mean X is 8. That's enough to get you the marks on the question. It's always quite nice, though, to just write out the formula at the bottom. Finishes the question off. A teacher noticed that a student had not cleared a large air bubble from the burette tap in preparing the burette for use before starting the titration. The air bubble was ejected during the first titration of the volumetric flask mixture. State the effect that this mistake would have on the value of the first titra. So the value would be higher than the amount of solution that had actually been added to the flask. State and explain the effect, if any, that this mistake would have on the average titra for the experiment. It should have no effect. The first titration usually isn't used because it's an accurate rough one. So normally we'd only use the second 2 titras. The maximum errors for the pipette and burette are shown below. These errors take into account multiple measurements. Estimate the maximum percentage error in each of these pieces of apparatus, and it gives you some values to use. So you need to remember that the percentage error is always the error in the equipment divided by the quantity used. And as it's a percentage, we're going to times it by 100. So for the pipette, the error in the pipette is 0.05. The quantity we used was 25. We need to multiply that by 100, and that gives us a 0.2% error. For the burette, the error is 0.15. The quantity that we have used is 24.25. Again, we're going to multiply that by 100 because it's a percentage, and that gives an answer of 0.62%. Silver oxide can be reduced by passing hydrogen gas over the heated oxide. The maximum mass of silver that could be obtained from 2.32 grams of silver oxide is... Okay, so the first thing we need to do is write a formula to see how they react. Once we've done that, we can work out the moles of silver oxide, which is going to be mass over mR. The mass is given to you in the question as 2.32. The mR is 231.8, so that gives us 0.01 moles. From the equation you can see it's a 1 to 2 ratio. Got 1 here and a 2 here. So the moles of silver are going to be 2 times the moles of silver oxide. And then you can work out the maximum mass, which is going to be moles times mR, or in this case AR because it's the relative atomic mass. And that gives you a total of 2.156 grams, which if we round up to 2 decimal places gives us answer D. Okay, so we need to work out the moles for each of these. So to get the moles for this first one, it's going to be the number of molecules you've been given divided by Avogadro's number, which gives us 0.1096. For this one, we're going to use mass over mR, which gives us 0.1031. For this one, we're going to rearrange PV equals nRT. So it's going to be N is equal to PV over RT. Pressure, remember you've got to convert into pascals. Volume is already given to you in meters cubed, so you don't have to convert that. R is the gas constant, and temperature has been given to you in Kelvin, so you don't have to convert that either. And that comes out at 0.100. And for this last one, it's going to be vol times conc, and it's in centimetres cubed, so remember to divide by 1,000, and that should give you 0.105. Okay, so the one that has the greatest number of moles is going to be the first one, which is A. Which of these pieces of apparatus has the lowest percentage uncertainty in the measurement shown? So remember, percentage error or percentage uncertainty is the error in the equipment divided by the quantity used, and then as it's a percentage you times it by 100. So you can work that out for all of these. So the first one, the uncertainty is 0.1. The volume or the quantity measured is 25. So that gives us 0.4. If we do the same for the others, we end up with 2.00, 0.67 and 0.43. So the one that has the lowest is going to be A. Okay, for this one, we know that we're trying to work out the total volume of gas remaining after 20 centimetres cubed of ethane are burnt completely in 100 centimetres cubed of oxygen, and we know that all volumes are measured at the same pressure and the same temperature. Right, we're trying to work out volume. So we can look at this using PV equals nRT. Now what we know is pressure is constant, so we don't have to worry about pressure. We know that R is a constant, it's the gas constant. And we know that T is going to be constant, it's kept the same. So that tells us that volume is directly proportional to the number of moles. So 20 centimetres cubed of ethene are going to require 3.5 times 20, which is 70 centimetres cubed of oxygen. Okay, so then all of the ethane has gone. It's reacted completely. The amount of oxygen remaining is going to be what we started with minus what's been used up. So we're going to end up with 30 centimetres cubed of oxygen remaining. We're going to have got 2 times 20 centimetres cubed, which equals 40 centimetres cubed of CO2 produced. And we're going to end up with 3 times 20 centimetres cubed, which is 60 centimetres cubed of water produced, because that's the moles ratio. We've got 1 to 2 and 1 to 3. And as we know moles are directly proportional to volume, we can just say that it's going to be 2 times and 3 times the volume. Okay, so the total amount of gas left over at the end is the remainder of the oxygen, what's been made of the carbon dioxide, and what's been made for water. So that gives us a total of 130 centimetres cubed. A sample of 2.18 grams of oxygen gas has a volume of 1,870 centimetres cubed at a pressure of 101 kilopascals. What is the temperature of the gas? So we're going to use the ideal gas equation. We want to rearrange it for temperature, so it's going to be PV over nR. So pressure we've got to put into pascals, so it's going to be 101,000 pascals. The volume has been given to us in centimetres cubed, so we need to convert that into metres cubed, so we're going to have to divide it by 1,000,000. Okay, N is the number of moles. Well, we haven't actually got the number of moles, but we have got the mass. And moles equals mass over mR. Remember, it's oxygen gas. Oxygen is a diatomic molecule, so it's going to be 2 oxygens together, which together would have a mass of 32, times the gas constant. And that gives us a temperature of 333.67, and remember it's Kelvin. If we round that up to the nearest whole number, we end up with answer B. In a blast furnace, the removal of silicon dioxide with limestone can be represented by the following equation. The minimum mass of calcium carbonate needed to remove 1 tonne, which is 100 kilograms of silicon dioxide, is. So we're going to work out how many moles of silicon dioxide we've got to start with. Now, as the final answer is in tonnes, I can leave my units in tonnes all the way through this. So I can do mass over mR and leave my answer as 1, and leave my number as 1. So that gives me 0.0167 moles of silicon dioxide. So I want to know how many moles I've got of calcium carbonate. And if you have a look at the equation, you can see it's a 1-to-1 ratio. So that's also going to equal 0.0167. So we now need to work out the mass of calcium carbonate, which is just going to be moles times mR. The moles we've got, the mR we need to work out, and the mR is 100.1. If we multiply those two together, we get 1.67. Don't forget, because we didn't convert it from tonnes in the first place, our answer is going to come out in tonnes. Really, if we're going to use mass over mR, we should have converted it into grams, but that same conversion would have cancelled out with the final conversion back into tonnes. So that gives us an answer of C. For the last few minutes of the video, I'm just going to let you see the mark scheme. So I'll go through this relatively slowly, but obviously you can use the pause function so you can check the answers and see how the mark scheme has shown the answers. And if you did have any problems with any of these questions and going through this video hasn't solved it, please make sure you bring the test to one of the workshops and we'll happily go through it with you. It's essential you understand all of these questions because any of these questions could come up on the end of year exam.